Hello there! Welcome to Lecture 33, Nuclear Physics and Radioactivity. While we've spent a lot of time discussing the importance of the mobile part of an atom, the electrons, we haven't really delved into the nucleus yet. This lecture will hopefully give you a better understanding of the inner workings of the nucleus and how it gives rise to radioactivity with both positive and negative consequences. Each of the following concepts will be discussed in this video: the atomic nucleus, radioactivity, alpha decay, beta decay, gamma decay, half-life, radiation damage and exposure, and artificial transmutation. As discussed in Lecture 11, the atomic nucleus is comprised of protons, positively charged particles, and neutrons, neutral particles. This was experimentally confirmed in the early 20th century with the Rutherford gold scattering experiment. Alpha particles, which are themselves positively charged, experienced very large deflections after being shot at gold foil when they collided with an atomic nucleus. This confirmed two things: that the nucleus of an atom was very compact and that it had a positive charge. We also discussed in Lecture 22 that like charges repel. Positive charges repel other positive charges. That's the reason why the Rutherford scattering experiment worked. So why is it that an atomic nucleus comprised of positively charged protons can stay together? Why don't they repel themselves apart? The reason that stable atomic nuclei stay together is that there is a force stronger than electromagnetism. That force is known as the strong force. The strong force acts over extremely small distances. Other than the fact that it is literally holding all of our constituent atoms together, we do not otherwise experience that force in our lives. It's not something that we can feel, like gravity, or experience, like electromagnetism. The strong force is the strongest of the four fundamental forces: the strong force, electromagnetism, the weak force, and gravity. As mentioned, over extremely small distances, such as that in an atomic nucleus, the strong force greatly overpowers the force of electromagnetic repulsion between protons. The presence of neutrons in atoms also helps with atomic stability. However, if an atom has enough protons, the size of the atomic nucleus becomes quite large. At a certain point, the size scale of an atomic nucleus may be larger than the strong force can operate within. These atomic nuclei are unstable and undergo radioactive decay. Elements more massive than lead, with an atomic number of 83 and up, all undergo spontaneous decay. Recall from Lecture 11 that isotopes are elements that have the same number of protons but different numbers of neutrons. Many elements have multiple isotopes. Some of those isotopes may be stable, and some may be unstable. Radioactivity refers to the decay of an unstable atomic nucleus. When the strong force is no longer able to hold together protons that exhibit electromagnetic repulsion, the atomic nucleus will break apart. In the late 19th century, Henry Becquerel discovered radioactivity when a sample containing uranium was left in a drawer and caused a photographic plate to become exposed. Scientists performed experiments and learned that whatever was emitted by the uranium could not be X-rays or other electromagnetic waves, because the particles emitted by the uranium could be deflected by electric and magnetic fields. This means whatever the uranium was spitting out contained an electric charge. This initial discovery unleashed a lot of new knowledge about atoms and isotopes. Unfortunately, before we learned about the negative effects of exposure to radiation, it also led to an enthusiasm for radioactive products, such as radium-infused water, that people would consume, not realizing that radioactivity is dangerous and can cause cancer and other health hazards in high dosages. Fortunately, our knowledge of radioactivity and radiation is much more thorough now that we've had more than 100 years to learn more about it. As we'll discuss to a small degree in this lecture, there are many beneficial uses of radioactivity in our lives. Medical sources of radiation can be used to diagnose and treat otherwise lethal conditions such as cancer. Carbon dating is used to determine the age of fossils. Scientists use radioactivity to create new atoms and isotopes. And smoke detectors use a radioactive source to detect the presence of smoke. There are 3 types of natural radioactive decay processes: alpha decay, beta decay, and gamma decay. Alpha decay is a process where an unstable atomic nucleus emits an alpha particle. An alpha particle is a helium nucleus, which is comprised of 2 protons and 2 neutrons. Alpha particles are the largest of the radioactive decay particles, and as such, tend to be emitted by relatively large unstable isotopes. During the alpha decay process, the total charge of all particles is conserved, as is the total number of nucleons in all of the particles. The composition of alpha particles was determined by using the magnetic deflecting force described in Lecture 24. The amount of deflection that a charged particle undergoes gives information about the mass. Because of inertia, a heavy particle will deflect less than a light particle. The amount of deflection of an alpha particle led scientists to calculate its mass. The direction of deflection has to do with charge. The deflection direction of alpha particles is consistent with a positive charge. Because alpha particles are so massive, they are very likely to lose energy when coming into contact with any other atoms. So while they are dangerous, they can be blocked by anything more massive than, say, a sheet of paper. It's therefore relatively easy to shield against alpha particle exposure. An example of alpha decay occurs when uranium-238 emits an alpha particle and becomes thorium-234. The atomic mass number is conserved. There are 238 nucleons in the original atom of uranium. The final atom of thorium has 234 nucleons, and the other 4 are present in the alpha particle. Atomic number, charge, is also conserved. The original uranium atom has 92 protons. The final thorium atom has 90 protons, and the alpha particle has the remaining 2. A cloud chamber is a device that can be used to visualize the byproducts of radioactive decay. In this video, lead-210 that is placed in the center of the chamber undergoes alpha decay, which generates condensation and can be visualized as trails of clouds emanating from the source. Beta decay is a process where a neutron in an atomic nucleus converts to a proton, and in that process emits an electron and a second subatomic particle known as an antineutrino. During this process, the total charge of all particles is conserved, as is the total number of nucleons in all of the particles. The magnetic deflection force was also used to determine the composition of beta decay. The amount of deflection of a beta particle led scientists to calculate its mass. The deflection direction of beta particles is consistent with negatively charged particles. Beta particles, being smaller than alpha particles, require thicker shielding to prevent exposure. However, it is possible to protect against beta particles by using several millimeters of aluminum foil, for example. An element that undergoes beta decay is thorium-234. An atom of thorium-234 will emit an electron and become proactinium-234. Note that the atomic mass number is conserved. There are 234 nucleons in the original atom of thorium and 234 nucleons in the final atom of proactinium. The atomic number, charge, is also conserved. There are 90 protons in thorium. There are 91 protons in proactinium, balanced by 1 electron. Carbon dating is used to determine how old organic archaeological samples are. All organic objects contain carbon. Living plants and animals will naturally replenish this carbon, which includes carbon-12, a stable isotope, and carbon-14, an unstable isotope. After death, the carbon-14 will no longer be replenished and will undergo beta decay with a half-life of 5,730 years. This means that the ratio of carbon-14 relative to carbon-12 in a fossil can be used to calculate its age. We'll discuss half-life in a few moments. An unstable nucleus that has undergone alpha or beta decay may be left in an excited state. Just as electrons can become excited and decay to a lower energy level, an entire nucleus can become excited and decay to a lower energy level. This nuclear decay process is known as gamma decay. And just as a decaying electron emits a photon, a decaying nucleus emits gamma radiation. Gamma radiation is simply a very high energy photon and is a form of ionizing radiation. Because gamma radiation is unaffected by the magnetic deflection force, it was shown to have no charge. Because it exhibits characteristics of electromagnetic waves, such as traveling at the speed of light in free space, it was determined to be part of the electromagnetic spectrum. Gamma radiation is very hazardous and also more difficult to shield against than alpha or beta particles. Gamma rays can be blocked with lead, concrete, or even large amounts of water. The decay process of unstable elements is characterized by something known as the half-life. This half-life is a description of the amount of time it takes, on average, for half of a particular isotope to decay. A decay process is probabilistic. A coin toss will probably result in an equal amount of heads or tails, but any individual coin toss may yield more heads than tails, or vice versa. Similarly, any particular sample of an unstable isotope may take longer or shorter than the known half-life. Every isotope has its own half-life. Xenon-124 has one of the longest known half-lives of 10 to the 22 years, much, much, much older than the known age of the universe. Scientists have detected the decay of Xenon-124 even though it is an extremely rare occurrence due to the extraordinary half-life. On the other end of the spectrum, a synthetic isotope of hydrogen, hydrogen-5, has the shortest known half-life of 10 to the negative 23 seconds. Because the half-life defines the amount of time it takes for half of an unstable isotope to decay, how long would it take 100% of an unstable isotope to decay? Let's say the half-life of an isotope is 1 day, and we have 100 grams of that isotope. After 1 day, approximately 50%, or 50 grams, of the sample will have decayed. After 2 days, approximately 50% of the remaining unstable sample, or 25 grams, will decay. After 3 days, an additional 12.5 grams will decay. This means that after 3 days, approximately 87.5% of the sample has decayed. After 7 days, 1 week, about 99.2% of the sample will have decayed. After 2 weeks, about 99.99% of the sample will have decayed. When does that value become 100%? The answer is that the decay process is asymptotic. We see that it approaches 100% over a long period of time, but the answer to the question of when does the very last atom of the isotope decay is completely probabilistic and cannot be definitively answered. Unstable isotopes with long half-lives that are present in nuclear waste or contamination can be particularly dangerous. This is because the long half-life indicates that a lot of time will have to pass before the isotope decays to a safe level. Even when the isotope does decay, it may decay to a second unstable isotope. It's possible that it will take days, years, decades, centuries, millennia, or longer for half of some radionuclides to decay to a stable isotope. The amount of radioactivity that humans encounter can be characterized by the energy we absorb by that radioactivity. This is known as RAD, radiation absorbed dose. 1 rad is equivalent to 0.01 joules per kilogram of tissue. However, not all radiation is equally dangerous. The unit of rem, Roentgen equivalent man, attempts to quantify the dosage of radiation based on the damage it causes to humans. Alpha radiation, for example, may only emit 1 rad, but has a health effect of 10 rems. Beta radiation of 1 rad would have a health effect of 1 rem. A lethal dose of radiation for a human starts at 500 rem, distributed over the entire body. Localized dosages of equivalent amounts of radiation may be survivable. While the concept of radioactivity sounds scary, the truth is that we're surrounded by it. There's a natural background of environmental radiation that we're exposed to in the air, from common rocks and minerals all around us. A small amount of radiation exposure is inevitable from our daily lives, and these small exposures pose minuscule risk in our lives. For perspective, a typical annual dose of naturally occurring radiation is about 0.3 rem, a very small amount. Medical diagnostics, such as CT scans and nuclear medicine, represent another source of possible radiation in our lives. The idea is that the benefit of the medical exposure to the radiation outweighs the risk of the radiation exposure itself. An isotope of radon, radon-222, is a heavy gas that may accumulate in basements that lack proper ventilation. High levels of radon-222 are dangerous, and radon detection and mitigation are both important to avoid unnecessary exposure to its alpha radiation. There are other sources of environmental radiation. Historical atmospheric nuclear testing occurred between the 1940s and the 1960s. Thankfully, it was banned in 1963, so the dosage we receive from this historical time period is fortunately decreasing every day. Occupational exposure is also possible. Jobs that may encounter exposure to radiation will require employees to wear dosimeters to track their exposure. Burning coal, for example, in power plants, leads to emission of radioactive thorium and uranium and is a larger source of environmental exposure to radiation than nuclear power plants. Nuclear accidents, such as Chernobyl and Fukushima, and nuclear waste are other sources of possible radiation exposure. One of the best ways to reduce your exposure to radiation is to quit smoking if you're a smoker. Cigarettes contain polonium-210, which undergoes alpha decay. When inhaled, it can represent a very large percentage of the annual radiation exposure of a smoker. The processes of natural transmutation have been discussed: alpha, beta, and gamma decay. But it's also possible to artificially transmute elements. Two particles can be smashed together to create a new atom. For example, helium-4 and nitrogen-14 can be artificially transmuted to oxygen-17 and hydrogen-1, a single proton. Just as with natural transmutation, in the artificial transmutation process, atomic mass number and charge are conserved. Long ago, alchemy was the study of transmuting elements such as lead into gold. It was hoped that a process could be found that would allow people to generate the precious metal. Today, it is possible to use artificial transmutation to create gold. However, it is not remotely economically feasible. This is because the amount of energy that goes into the production of gold is enormous, and the gold that is created in the transmutation process has to be the one isotope of gold that's stable. Otherwise, it will naturally transmute into other elements. Artificial transmutation has been used to generate atoms that don't exist naturally. The so-called super heavy elements on the periodic table that have an atomic number greater than 103 have only been created in laboratory settings. These isotopes have such short half-lives that if any natural sources existed, they are long since decayed. The creation of these elements leads to advances in physics and chemistry. Artificial transmutation is also used in radiopharmacology to generate isotopes with short half-lives to use in medical treatment or diagnosis. Some elements, such as technetium-99, need to be generated almost immediately before use, as the short half-life would otherwise cause them to decay almost entirely before their use. Thanks for taking the time to learn about nuclear physics and radioactivity. Until next time, stay well.